All right. Thanks everyone for tuning in. My name is Christopher Bendixson. I'm the head of research at CoinShares. We're a crypto investment firm, a digital asset manager. We got a full suite of crypto investment products that I'm not going to talk too much about here because I don't actually have time, but you can check us out on our website. I'm going to talk about Bitcoins and renewables. Let me run about this all the way back. Sorry, I was at the wrong end. We're going to talk about Bitcoin and renewables again. I'm going to follow up a little bit on some of the previous points that Philip made. I'm going to come at this from a little bit of a different angle, but it's not actually that different what we're going to talk about. As many of you have seen, for quite some time now, the media has been claiming that Bitcoin mining is an exceptionally damaging industry with regards to the climate. And it's even gone so far as certain people publicly asking that governments ban Bitcoin entirely to, quote unquote, save the environment. I don't have time to cover any of those articles or their contents in full detail, but I've still collected my favorite quotes, though. So we have Bitcoin mining may be pumping out as much CO2 per year as Kansas. Could be. Bitcoin predicted to be the nail in the coffin of climate change. Yeah, okay. Bitcoin can push global warming above 2 degrees centigrade in a couple decades. No. And then just my favorite. Bitcoin will burn the planet down. The question, how fast? So in this pretty quick presentation, I'm going to make 2 points, and I'm going to add my own opinion as a conclusion. First, I'm going to show that Bitcoin mining is probably nowhere nearly as bad as some of these pundits are claiming. And in fact, it's our belief that Bitcoin mining is predominantly driven by renewable energy. Secondly, I'll claim that exactly contrary to what's being said, Bitcoin mining is an excellent opportunity for mankind to effectively increase the investment in renewables projects without having to involve neither taxpayers nor governments. And so if they actually want a positive outcome for renewable projects, is my conclusion, governments should simply leave Bitcoin alone. So the anti-mining argument goes something like this, simplification. So Bitcoin miners are predominantly located in China. That's true. China mainly generates its electricity from coal. That's also true. Therefore, Bitcoin mining is predominantly driven by coal-based electricity. We don't think that's true. We think that's false. And I'll get into why we believe this last one is false, but let me first talk a bit about how we got there. So when we were first introduced to this narrative, and this is quite a few years ago, actually, we were concerned too, because it is true that Bitcoin uses a lot of energy. But as we started looking a little deeper into the actual mining industry, it also became increasingly clear that the dirty industry narrative is built on somewhat shaky grounds, and it's based on methodologies that we consider to be not quite appropriate and not sufficiently granular. So almost all the large miners we spoke to initially were hydro miners, and there's a greater diversity now. So it already smelled a bit funky from the start. So we started putting together an overview of the most important global mining regions. And the way we did this was to trawl the internet for any public announcement of mining facilities. We read all available mining research we can find. We lurked around tons of mining forums, chat groups, called, emailed, and texted pretty much anyone that would answer us, which initially weren't a lot of people, but 2.5 years in, more and more these days. So it turns out there's actually quite a lot of information out there. It's just very scattered and hard to collect. So it's extremely time consuming, which is why I don't think there's been that. I mean, there's a lot of good research coming out now, but back then there really wasn't a lot. But here's where our estimate currently stands. So as you can see on this map, there are concentrations of miners in the Pacific Northwest, Texas, Eastern United States, Canada, Iceland, the Nordics, Caucasus, Iran, Russian Southern Siberia, Kazakhstan, and certain provinces of China. Some very interesting patterns here. A lot of miners are in mountainous regions, and a lot of these regions are traversed by powerful rivers. Many are in regions that are windy, and many are in regions that are relatively sparsely populated. Some are in regions where fossil fuels are extremely cheap and abundant. And I also do have to make the point that mining on waste gas from North American oil fields here has enormous potential for future development. Marty will tell you all about that. It's just not something that we've seen fully come to fruition yet. It's on the cusp, though, which you know, we'll talk a little bit about that. On top of this, though, a lot of these regions had relatively high renewable curtailment rates, and this was particularly true within China. We already knew that mining is incredibly competitive, and that the pressure on miners to access cheaper and cheaper electricity is extreme, as Philip mentioned in his presentation. Having come from an energy background, I also knew that, contrary to what a lot of people think, renewables are often the cheapest sources of electricity available, especially hydro, geothermal, and onshore wind. It's just that they tend to be in unfortunate locations, on top of mountains, like Philip said. So, wind, rain, and volcanoes can't really be shipped around the world like coal and gas can. Renewable power plants need to be built wherever their geography allows them. So one of the main problems we face with renewables, not even considering the variable production issue of solar and wind and the side effects that has on the grid, one of the main problems we have is transmission losses. So when we send power over long distances, some is lost as heat, and the problem increases with distance. If the renewable power plant is far enough from demand centers, the transmission losses can be so large that by the time the electricity reaches demand centers, it can't actually compete on cost against fossil fuel plants, which can be placed right next to its clients. Not to mention that long distance transmission lines are also expensive, they're unsightly, and unpopular. Someone has to pay for them, which are the consumers, through higher prices. Nobody wants them in their backyard, and nobody even wants to look at them because they're ugly. This is simplifying a complex subject, but transmission losses are a major reason why we can't power more of the world with hydropower, even if we have huge untapped capacity all over the world. I mean, I would know. I'm from Norway, and we have so much of this stuff laying around. We just have, we just don't know how to sell it. By the time it reaches industry or consumers, it's just too expensive. So again, contrary to what a lot of people think, we don't really send electricity over long distances in large quantities. It's just not economical. And this makes a lot of renewable energy stranded, and it also mutes the argument that renewables spent on mining simply necessitates the addition of fossil fuels somewhere else. That's just not how it works. So at the source, on a localized cost of electricity basis, hydropower is the cheapest 24/7 available renewable energy in the world, and we have a lot of it. So this is an overview of localized cost of energy for global utility scale power projects. So that is the total cost of electricity per megawatt over the project lifetime. As you can see, geothermal, onshore wind, and hydro generate some of the cheapest electricity available. And this even underestimates hydro projects because they tend to outlive their projected lifetime and can be refurbished extremely cheaply compared to their construction cost, which is mainly the cost of the dam itself. So to add to this, lots of large and mid-scale hydro dams do not run at capacity. Sometimes because of seasonality, often because they're too far from demand centers, other times because they were built in the absence of corresponding grid capacity, other times again because industry or consumers they were originally built to serve has since left or never arrived, but the dam is still there. So in fact, absurd amounts of potential energy is wasted globally every year by letting water run over dams, mostly in China, which is by far the world's largest producer of hydropower. And this is a massive drain on profitability of renewables. So Reuters estimated in 2015 that around 1,000 terawatt hours were wasted in China. That's enough to power Britain and Germany combined. Yunnan Governor Reng Chengfa said his province wasted 30 terawatt hours annually in 2018. The reason I mentioned Yunnan specifically is because it's a big Bitcoin mining region. Same with Sichuan, another big Bitcoin mining region that had 75 gigawatts of installed hydropower capacity in 2017, but its grid can only handle half of that. And for context here again, the Bitcoin mining network currently draws around 8.4 gigawatts, or around 73 terawatt hours on an annualized basis. So with all of this in mind, we started looking at the mining regions in more detail with regards to their energy mix. So even if our methodology is a little bit more granular, it's still very simple. For smaller countries like Iceland or Georgia or Norway or Sweden, we figured it's pretty reasonable to assume that any miner within the country would use roughly the same energy mix as the national average. But, and I think this is extremely important, for larger countries like China or Russia, the US or Canada, regional differences in renewables are so big that assumptions like that don't actually work. Like the energy mix in Texas is not the same as in Oregon, nor is it the same in Xinjiang or Sichuan. They might as well be different countries. Sometimes they even have their own grids, like Texas. So for these large countries, we found the renewables penetration in each localized region, and we used that instead of national averages. So here are the regions that we, in 2019, found to be the most important ones. As you can see, we selected 4 particular regions out of China, and then a whole host of various countries and provinces and states on the east side. You'll note here that most of these regions have a much higher renewables penetration than the global average of 18%. And so in this model, we group them into 4 groups. So we have Sichuan and then remaining China, which is Yunnan, Xinjiang, and Inner Mongolia. Then we have the remaining non-relevant Chinese regions, which are all the countries in the right column, and then we have the rest of the world. So inside of the groupings, we simply take an arithmetic average of all participants, and we do that just to reflect the fact that these are estimates, right? I want to just point that out, just like Udi did. These are estimates, and we don't want to make the model seem more detailed than it is. So using these, in December, we calculated this renewables penetration, which was even on one of Philip's slides. So the way we do that is that we take the renewables penetration of each of those regions, and then we add the global mining share to it. And so global mining share, we think, is approximately 65% in China, with 80% of that in Sichuan. And the remaining non-Chinese regions account for around 31%, and then 4% scattered around the world. So in this case, the renewables estimate is 73%. However, there is a really important caveat to this table, which we've come to realize over time. It reflects the conditions of the last Chinese wet season. So let me talk a little bit about that. The more we learn about local dynamics within China, the more we've realized it's not quite as straightforward as our initial estimates might suggest. So whereas in the beginning, we thought that mining operations, when established, were fairly static, and that is indeed the case in almost the entire world, but it is not the case in China. So in fact, the Chinese mining industry is highly seasonal. And this is a result of seasonal weather causing the electricity prices to fluctuate in the hydro-heavy regions in the southwest. So the wet season starts in the late spring and it lasts until late fall, approximately May to December. And during the wet season, electricity is cheapest in Sichuan and Yunnan, which are hydro regions. And in the dry season, it is cheapest in Xinjiang and Inner Mongolia, which are coal and wind regions. So to take advantage of that, miners migrate. So they migrate between the largest purple dot and the almost black dot. I don't know if I'm colorblind. So, for those that wonder, that's almost, I think it's actually 2,000 kilometers. So we have potentially gigawatts of miners moving thousands of kilometers twice a year. Think about that. That's pretty crazy. And also, to be clear, we know these migrations happen, but we're not yet quite sure of the extent. There's some really sexy data recently released by Cambridge, Apolline Blanding's team, that suggests that it's actually pretty extensive, so much more common than we first thought. And since last December, unfortunately, we haven't had the opportunity to make a comprehensive estimate of miner locations this year. But what we've gotten instead are those Cambridge figures suggesting that the vast majority of internal Chinese miners might actually move around with the seasons. So instead of doing a proper new estimate, I figured I'd instead show you what the renewables penetration would look like under the assumption that during the wet season, 80% of Chinese mining happens in Sichuan and Yunnan, like our December estimate. And in the dry season, it's 80% Xinjiang and Inner Mongolia, which looks a lot more like the current image suggested by that Cambridge data. So here we've just adapted our methodology slightly. Our 4 groups are now Sichuan and Yunnan, that are now wet season China. And then we have Xinjiang and Inner Mongolia, which is dry season China. And then remaining relevant global mining regions and rest of the world. So for mining shares, we've assumed the same international distribution as before, 65% China, 31% remaining world, and 4 in the scattered among the non-important regions. And internally in China, we've assumed that 80% of Chinese hash rate flows between Sichuan, Yunnan in the summer and Xinjiang, Inner Mongolia in the winter every season. And so the current dry season renewables penetration estimate looks like this, where the share of renewables for mining is 41%. So as you can see, it has a really large effect. And the current wet season estimate would be 69%, and that is even down from what we had earlier, and that reflects increased mining in Kazakhstan and other, Iran, which has essentially zero renewables, which would put the annual renewables average at 55%. And considering the fact that the seasons are roughly 6 months each, that's how we would target that. So I think that it is likely that the truth is closer to the average of the two, but frankly, we need more data to be sure. And the fact that it changes so rapidly is a big challenge for us, which is why the approach that they've taken at the Cambridge Center is super, super interesting. Also, for a truly full view, we need county level renewables figures in places like New York and Texas, because we know that miners tend to operate, for example, way upstate in New York, where there are very few people, very far from the population centers on the St. Lawrence Basin, where it's almost entirely hydro-driven. And in Texas, they tend to operate inland away from the cities as well, in wind region, but also on natural gas. So, in any case, even under these assumptions, renewables are the main driver of mining. And again, back to what Philip is saying, it's a cost issue. It's because they are cheaper. And the share of renewables in the mining energy mix is still multiples above that of the global average, which leads me to the final point I want to make. So Bitcoin mining acts as a global electricity buyer of last resort. If you're in a country with at least decent property rights and with a semblance of political stability, and you can produce and sell electricity at, call it like 3 cents a kilowatt hour, you will have instant demand from miners. Nick Carter made an excellent mental image of this a few years back. He imagined global electricity prices as a surface relief map. And on this map, the peaks would represent the high electricity prices and the bottoms or troughs would represent low prices. And mining acts as a glass of water poured out over this map. It seeks out the bottoms and it smoothens it out. So this means that we can use mining to bootstrap renewables projects that are otherwise too remote to warrant initial investment. Instead of having to front load the entire project with enough capital to immediately connect it to the grid, miners can come in, sit right on the site, and monetize that electricity immediately. So as soon as the renewables project itself reaches certain ROI goals, return on investment goals, it can be refinanced and connected to demand centers. Miners can move on to the next project, and the end result is cheap renewable energy for industry and consumers. No need for subsidies, just the free market doing its thing. Keeping in mind that the energy sources with the lowest levelized cost of electricity are renewables, particularly onshore wind, geothermal, and hydro, what we're effectively doing then is a voluntary redirection of capital from savers to renewable energy projects, increasing investment in that sector, and all at the same time safeguarding a globally independent hard asset monetary system. And that's something I think we should take the time to think about with a little more depth and nuance. Thank you very much.